webinar. My name is Xuemei You from Editorial Office of Journal Theoretical and Applied Mechanics Letters, abbreviated as TAML. It's my honor to start this webinar. Before we delve into today's stimulating discussions, please allow me a moment to introduce both our journal and today's webinar. TAML aims to publish cutting-edge research in theoretical, computational, and experimental mechanics, emphasizing originality and rapid dissemination of advances in science, engineering, and technology. The impact factor for this year stands at 3.2, with a science score of 6.2, reflecting the high quality and relevance of our published research. We ensure swift publication with an average time to first decision of just 3 weeks, facilitating timely exposure of groundbreaking work to the academic community. TAML is led by Editors-in-Chief Professor Guowei He and Professor Yonggang Huang. Our dedicated team consists of 75 editors and board members from 17 countries, all affiliated with prestigious universities and research institutions. This diverse expertise ensures that TAML maintains the highest standards of academic excellence and integrity. We are committed to providing exceptional support to our reviewers, authors, and broader community, guiding you through every step of the publication process with our extensive expertise. We warmly invite you to consider submit your research to TAML and join our growing committee of contributors. Let's move on to the next slides to introduce the specifics of today's webinar. Thanks. This webinar is jointly hosted by TAML, Elsevier, the Chinese Society of Theoretical and Applied Mechanics, at the National Nature Science Foundation of China Basic Science Central Program, focusing on multi-scale problems in nonlinear mechanics. Our goal is to offer an international platform for researchers to communicate and share their latest work, fostering, collaborating, and advancing knowledge in our field. You can follow the webinars through our web pages on Elsevier and CSTA app, to our WeChat group via the provided barcode, or follow us through our other communication channels for continuous updates. Finally, I would like to extend my heartfelt gratitude to everyone involved in making this webinar possible. Special thanks go to today's speaker, Professor Jinqiang Zheng, and today's webinar host, Professor Jun Zhang. Your contributions are invaluable to the success of this event. Thank you for your attention, and I look forward to engaging and informative webinar. Now, I would like to pass the baton to our webinar host, Professor Jun Zhang, who will take us through the next section of our webinar. Professor Zhang, over to you.
Okay, great. Greetings. I'm honored to be asked and to host this special talk, this online talk by Jinqiang Zheng, a professor of Fudan University. Let me briefly introduce him. He graduated from Fudan a long time ago, around 2001, and then went to New York University Physics Department, spending 5 years, finished his PhD in physics. He started thermal convection over there, and then he moved on to UC Santa Barbara with Gunther Alles. And adding to thermal convection, he started at NYU, he added rotation. So as you could probably guess, this addition has a niche that is meant to be simulating the system such like Earth. You know, the Earth is a very sophisticated system. It rotates and it controls thermal convection. And after that, he moved on to Yale University, spent like 2-3 years as a research scientist, came back to China, to Tongji University for 11 years. And now, in the last 2 years, he moved to Fudan. Okay? And over the years, Jingqiang has earned his quite a few recognitions, like the Young Talent Program. And recently, 2 years ago, he got this one-ren program, like the 10,000 program. Okay? It's a big recognition. And today he is going to tell us the dynamics of vortices in rotating Rayleigh-Bénard system. And he has roughly 40 minutes. During his talk, if you want, you can raise your hand or also put questions in the chat room, in the chat, so we can read at times, but without interrupting his talk, we have a tendency to ask those questions at the end of the talk. Okay, Professor Zong, please take the floor. It's all yours. Thank you.
Thank you very much for the introduction. Thank you all joining us in the TAML seminar today. I'm grateful for the opportunity to introduce the research work of dynamics of vortices in rotating Rayleigh-Bénard convection. It's a collaborative studies in the past few years by my lab and by Dr. Xia's group. Rotating convection is relevant to manage physical and astrophysical phenomena, as Professor Zhang just introduced. It's also a rapidly developing field that has caused much research interest. The subject I will discuss in this talk, vortices, is a popular form of vortex of fluid motion in nature. Vortices can be found in daily life, such as in a coffee cup, in a plug hole. It arises in the atmosphere, in the ocean, and it gas planets. Hurricanes and typhoons are large-scale vortices that might cause serious natural disaster. How to predict their motion, prevent them from destructions are of significance. In this slide, I show some observation data of hurricanes occurs in the East Pacific Ocean and in the Atlantic Ocean. We see very different trajectories, moving speeds, strengths of hurricanes. These data are available at the NOAA website. In the viewpoint of fluid mechanics, there are two mechanisms responsible for the formation and evolution of these tropical vortices: thermal convection in the air and the rotation of the Earth. In laboratory, we studied vortex dynamics in rotating Rayleigh-Bénard system. In this model, a fluid layer is heated from below, cooled from above, and rotated about a vertical axis. We use two main parameters to control the fluid motion: Rayleigh number that represents the strength of convection. Ekman number represents the strength of rotation. If the rotating ray increases, the main flow structure changes from a single row circulation into multiple columnar vortices. In the limit of rapid rotation, the Taylor-Powderman theorem predicts that the fluid velocity is vertically invariant. Let's discuss the equation of fluid motion with strong rotations. We consider a steady solution far from the viscous spongy layers, so we can neglect the inertial force, the viscous force. Then the correlated force is balanced by the pressure gradient in the horizontal direction. If we take the derivative of this equation and make use of the fact that the fluid is incompressible, we obtain the thermal wind balance. That is, the vertical velocity gradient is caused by horizontal temperature variations. If the correlated force dominates the Buoyancy force, we finally arrive at the TP theorem, which states that the vertical velocity gradient is zero. The right figure shows DNS data of the temperature distribution of these convective vortices. As predicted by the TP theorem, we see the structure of these convective vortices is independent on the fluid height. But the question we pursue here is that what's the dynamics of these columnar vortices? How is their translational velocity depends on rotation and buoyancy. These are fundamental questions of research interest. In previous studies, scientists have observed these beautiful kinetic vortices. In 1997, Sakai report Tilly columns continuous advection devoid of merge or collision. But the Lusher group observed these regular kinetic vortex grids that can be stationary for one working day. In 2010, the UCLA group reported the stochastic motion of vortices like horizontal dancing. These descriptions are all quantitative. But how do we understand the different dynamics of these kinetic vortices? In the research field of rotating convection, intensive study has been devoted to explore how rotation suppress the onset of convection, how it changes the viscous boundary layer, modify the shape of thermoplume structures into kernel vortices, and how rotation suppress or enhance global heat transport. The dynamics, and particularly the horizontal motion of the kinetic vortices, remain unexplored. In this context, we construct high-speed rotating convection operators to study vortex dynamics. Here is a schematic drawing showing the experimental design. We use a cylindrical cell of diameter 24 centimeters. Its bottom plate is made by high conductivity copper with its temperature well regulated to within a few millikelvin. 3 thermal shields are made surrounding the fluid. They isolate the system from ambient temperature fluctuation and ensure precise measurement. The apparatus is dedicated for high-resolution flow visualization. A sapphire window is made on the top plate, and a horizontal laser sheet is projected onto the fluid, illuminating the sealing particle. A rotating camera captures the flow motion from the top sapphire window. The whole apparatus is built on a fast rotating table. The space volume in this shade color rotates with the table during the experiment. The right photo shows the real scale of the setup. Let's watch an experimental video. What we've seen is a top view of the vorticity field. The color represents the strength of the vorticity, where the red and blue patches are cyclones and anticyclones. Here we choose a relatively slow rotating rate, Ekman number 3.3 times 10 to the negative 5. We see these kinetic vortices are moving horizontally in a similarly random manner. During their motion, each vortex seems to maintain a certain distance from its neighbors. But when two vortices of the same type, such as two cyclones, will try to converge into a strong cyclone. In the long run, the motion of the vortex is similar to Brownian random motion. From this velocity data, we can keep tracking of the vortices and reproduce their trajectory. We calculate the mean square displacement of the vortices as a function of time the vortex traveled. We found that for different rotating rate, the mean square displacement undergoes a transition from a Bliss regime, where it increases as a quadratic function of time, to a diffuse regime where it increases linearly. So these results suggest that the motion of the vortices in this flow regime is Brownian type random motion. We have two important experimental findings here. First one is that the transitional time between Bliss regime to diffuse regime, tau, is about 10 seconds. It's a very uncommon translational time. We know in stochastical mechanics that the transitional time for the Brownian motion of microscopic particles is only a few microseconds or even shorter. So it has been very challenging to study ballistic motion in statistical mechanics. The fact that the transitional time for vortex motion is 10 seconds brings to us the possibility to study ballistic motion under regular experimental settings and to investigate diffuse motion in a time scale of 10 minutes. The second important finding is that if we normalize the time by the translational time tau, normalize the MSD by diffusivity T times tau, we found data for different parameter collapse onto one single curve predicted by linear equation. This type of random motion is known as pure Brownian motion, a quite remarkable prediction by Rayleigh-Bénard a century ago. In this slide, I give you some details about Brownian motion in statistical mechanics. Contemporary study of Brownian motion began with Einstein in 1905. In 1908, Rayleigh-Bénard established the equation of motion for Brownian particles. He predicted that the MSD of the particles increases as a t squared at short time, increases as t for long time. This kind of random motion is called pure Brownian motion. However, in reality, when the particles move in a fluid, it will retreat the fluid, and the fluid reacts back to the particle. Such a hydrodynamic memory effect will lead to a broad transition from diffuse regime to from bliss regime to diffuse regime. There exists a very broad range for transition. So indeed, pure Brownian motion has not been observed in real fluid systems ever since Rayleigh-Bénard's work. In our vortex system, vortices are viewed as coherent structures like particles. When they move in a background of turbulence, the reacting force from the surrounding fluid is dominated by turbulent fluctuation that can be modeled by random noise. So in this system, there's no hydrodynamic memory effect. The motion of the vortices is well described by the Rayleigh equation that consists the inertial force, the viscous force, and the random force originated from the background turbulence. For this reason, we found the mean square displacement undergo a sharp transition from the bliss regime to the diffuse regime. We further find that the velocity correlation function decays as a pure exponential function. These results suggest that the vortex motion we observe is a pure Brownian motion. In the next session, I will introduce a new type of vortex motion in a flow regime where the centrifugal force is significant. Here's another experimental video captured at a rotating rate of 0.5 Hertz, and the float number, which measures the ratio of the centrifugal force over gravity, is 0.12. Under these conditions, we see the cold vortices represented by the red patches are moving outwardly, although their motion are frequently disturbed by labeling vortices, and the warm vortices are moving inward. If we look into the trajectory of the vortices, we see clearly they undergo radial motion. Such a directional motion leads to super diffusive behavior. Their mean square displacement in the diffuse regime increases faster than a linear function. If we look into the vortex trajectory, we found that radial velocity increases in time. This type of motion is similar to centrifugal motion. If the centrifugal force is significant, then additional term appears in the equation of fluid motion. The centrifugal buoyancy is proportional to the radial position r, also proportional to the density difference between the vortex and the ambient fluid. Here is a cartoon drawing that shows the status of vortex motion. The warm, lighter vortex is subjected to a centripetal force and moves towards the rotating axis, while the cold, heavier vortex is driven away by centrifugal force from the rotating axis. Meanwhile, the background turbulence apply a random force on these vortices. So the motion of the vortices can be viewed as random motion in a parabolic potential well. Is attractive for warm vortices, repulsive for cold vortices. And a linear equation incorporating the centrifugal force should be capable to describe the vortex motion. We show this stochastic differential equation and find out the first order and second order radial displacements. These quantities represent the mean trajectory as a function of time of the vortices, and the variance of the vortex trajectories with respect to their mean path. In theory, these quantities are all summation of exponential functions. Here we compare the modeling results with the experiment. The open symbols are the experimental data, and the solid curve are the model predictions. On the left figure, we show the second order displacement for cold vortices. We found the model captured satisfactorily the data trend that the second order displacement first increases as a exponential function of time at short time. Its increasing rate first decreases and then increases, and finally approach another exponential function at large time. For the warm vortices, the model also predicts correctly the data trend that the second order displacement approach to a constant at large time. And the inset figure shows the first order displacements. The close agreement with the modeling result and the experimental data suggests that vortex motion in this flow regime can be well described by centrifugal force-driven stochastic motion. So far, we have discussed the Brownian motion, centrifugal motion of the vortices, where the vortices are viewed as single isolated ones, separated from other vortices. However, in many lateral flows, vortices appear as densely populated states. Examples include the macroscopic vortice in the ocean and the polar vortice in the gas planets. To explore the dynamics of densely populated vortices is thus important for us to understand this lateral phenomena. In rotating convection, there exists a one-third law for the length scale of the vortices. The horizontal length scale of the vortex L is proportional to Ekman number to the power of 1/3. The number density N is proportional to the rotating rate to the power of 2/3. Here's another experiment that shows the vortex distribution under rapid rotations. By the way, this 1/3 law suggests that the fast rotating is the table, the vortices will become smaller and denser. Here we use blue and yellow circles to denote the center of the cold and warm vortices, and the background color represents the Q value of the velocity field. We see that under rapid rotation, the vortex indeed becomes smaller and denser. Labeling vortices often have similar rotating velocity. They move collectively, forming vortex clusters. Closer inspection also shows that the warm vortices often subject to the motion of the whole cluster and move outwardly. It's opposite to the centrifugal motion. The formation of large-scale vortex clusters and the inverse centrifugal motion of the vortices are new experimental findings. Here we use two criteria to identify vortex cluster. First, the vortices are closely packed. Inside a cluster, two labeling vortices has a distance less than 1.5 times their mean diameter. Second criteria is that motion of two vortices in a cluster are similar to each other. The angle difference between the velocity vector of two labeling vortices is less than 60 degrees. The right figure shows 6 large-scale vortex clusters found at one time. We first studied the size distribution of the vortex clusters piece band. That's the possibility to find out vortex cluster consisting n vortices. For small n, we found p sub n is a power function, but for large n, p sub n decays exponentially. So p sub n is a power function with its exponential tail. We found the power exponent b is negative 3/2. It suggests that the formation of vortex clusters is through a process of local vortex aggregation. To gain some more insight into the formation of vortex clusters, we studied the vortex interaction and look into the vorticity profile along a radius of an anticyclone. We found omega can be described by oscillating function. Its maximum at the vortex center, it clocks 0 at the vortex edge and reach a local minimum outside the vortex core. So a strong vorticity gradient is created outside an anticyclone. The series of vortex dynamics suggests that nearby cyclones will move towards the position where the vorticity is minimum. So we found the PD of the vortex number has a prominent peak where the vorticity is minimum. Such a vortex interaction leads to aggregation of vortices and the formation of vortex cluster. In many geophysical biological systems, such as bacteria, birds, frogs, the motion of densely populated units seems complicated, but they often present long-range correlative motion, forming biological clusters. People found that the correlation function of individual units follows a stretch exponential function, and the correlation length scale is simply proportional to the cluster size. In our vortex system, we calculate the correlation function of vortex velocity fluctuation. When two vortices inside a cluster are close to each other, their velocity are similar. So their correlation function is a large positive number. We found the correlation function decreases when the vortex distance increases. When it clocks 0, the vortex separation LC is defined as the correlation length. We found the correlation length of vortex motion increases when the cluster size increases. However, if we normalize the distance by the horizontal length scale of the vortex cluster, capital L, we found the Cox correlation function for different cluster size collapse onto a curve represented by a stretch experimental function. And the correlation length happens to be certain percent times cluster size. This result shows that although the motion of densely populated vortices are complicated, their motion are long-range correlated and scale-free. We have seen very rich dynamics of vortices. In the last section, I will introduce an experiment that controls the vortex motion through external forcing. In the last century, G.I. Taylor observed columnar vortices above a rigid cylinder in a rotating fluid tank. The Taylor column he observed is a coherent structure, very robust against external disturbance, which can be interpreted again by the Taylor-Powderman theorem. The vertical fluid velocity initialized by the rigid cylinder can penetrate through the fluid layer. In rotating convection, can we similarly introduce new structures to control vortex motion by external forcing? We use a convection apparatus described before, but construct on a bottom plate with an array of thin cylinders. These cylinders are periodically spaced to form a hexagonal or square texture. The cylinders are 6 millimeters in diameter, a similar size as the vortices. They are 3 meters at height, extending out of the bottom surface. Our experiment shows that when these thin cylinders are constructed on the bottom plate, they can determine the convection pattern and control the vortices. In a regular cell, when these cylinders are absent, we see again the random motion of the vortices. Since each vortex maintains a certain distance from its neighbors, in the Fourier spectrum of the vorticity field, we see a ring structure with a radial K0 representing the mean vortex spacing. When the button plate is textured with a square or hexagonal array of cylinders, they modulate the fluid temperature and velocity. Since the fluid temperature above the raised cylinder is relatively hot than the ambient fluid, warm cyclones tend to form above each raised cylinder, forming a 1+1 constant structure with respect to the button texture. We see such a regular pattern stationary and persistent despite the traveling wave on the domain boundary. From the Fourier spectrum of the vortice field, we see clearly maximums at wave vectors representing the imposed texture. The physics of pattern formation has been studied in the past few decades. People observe beautiful and regular patterns near the onset of convection. In the case of a non-rotating convection, the flow pattern consists of cells and parallel rows. But in rotating convection, either cells or row structures are prohibited by the collinear force, while the columnar vortices are favorably structured. So the pattern in rotating convection consists of these vortices. Experimental effort has been made to study pattern selection in non-rotating convection through external forcing. Very few work has been studied modulating flow pattern consisting vortices. In this sense, our experiment is an interesting attempt, and we hope it can inspire future studies. In the experiment, there are two controlling parameters, Rayleigh number and the horizontal spacing of the vortices of the cylinders. We first choose a constant cylinder spacing d, which is close to the mean vortex spacing lambda 0. When we increase the reduced Rayleigh number, we found the vortices change gradually from regular lattice to a random distribution. On the other hand, if we choose the Rayleigh number but increases the cylinder spacing, we see the motion of the vortex also change from a stationary state into a freely random moving state. We calculate the Clock's correlation function of the vortice field and the button texture as a function of these two control parameters. We use a binary max function mxy to describe the button texture. So the Clock's correlation function C represents the degree of overlapping between the vortice field and the button texture. The higher value of C reflects a better overlapping. On the right figure, we show in the phase diagram of epsilon and the modulation wave number kf, the value of this Clock's correlation function. We found the Clock's correlation function has a maximum when epsilon is about 0.5, and the modulation wave number is equal to the mean wave number of the vortices. This is the optimal control parameter we can use to modulate vortex motion. Varying these control parameters will reduce the correlation function. We studied the vortex motion with varying thermal forcing. Here, the red and blue lines represent the trajectory of the warm and cold vortices, respectively. With a strong thermal forcing when epsilon is 4.18, we found the vortex motion is not affected by the button texture. It inhibits random motion. When the thermal forcing decreases, the modulating effect becomes noticeable. We see the warm vortex tends to stay above the raised cylinder, while the cold one moves around them forming web-like trajectories. When epsilon reduced to be 0.5, we found the warm waters is strictly confined above the raised cylinder, while the cold ones are restricted in the middle of them, forming a regular vortex grid. We calculate the mean square displacement of the vortices. When Rayleigh number decreases, we found the MSD decreases monotonically. For warm cyclones, we see that the vortex exhibits subdiffusive behavior in the diffusion regime. We calculate the effective diffusivity using the green combo formula. We found the diffusivity decreases rapidly when epsilon is close to 1. So the vortex motion can be described as modulated Brownian random motion. It's a brief summary of my talk. We report very rich dynamics of vortices in rotating thermal convection. Under weak rotation, the vortices undergoes pure Brownian motion driven by the background turbulence. With strong rotations, the vortices becomes densely populated, and they undergoes long-range correlated scale-free collective motion. By external focusing, we can modulate the vortex motion and observe regular vortex lattice patterns. I would like to acknowledge my college. They have great contribution for the previous research. And thank you for your attention. I'm happy to take your questions.
Okay. I guess Jingqiang finished a little early. That leaves us plenty of time for questions and remarks. By the way, with Jingqiang, we are only 15 kilometers away, right? Where are you sitting?
Yes.
Are you sitting in Fudan right now?
I'm in Fudan.
Okay, right. I'm in Pudong at NYU Shanghai. Okay.
I might see your building though, because I'm at a very high level of the Guanghua building.
Okay. Questions? Let me open the chat. Let me see. Yeah, let me start with a simple question. At the beginning of your talk,
Yes.
We saw the vortices are moving, and they seems to follow two different behaviors. One is ballistic, the other
Yes.
one is diffusive, and the crossover time is something like 10 seconds.
Yes.
What is this 10 seconds mean? That's
Yes.
you know.
Yes. That's
yeah.
an insightful question, and I have to do some very rough calculation to explain how come we have such a long translational time of the vortices between ballistic regime and diffusive regime. So if we write down the Legion equation to model the vortex motion, and we divide the max term, then we can derive the transitional time Tc, which is given by the stroke coefficient gamma, and the radius, the stroke coefficient gamma contains this radius of the vortices. It also depends on slightly the density difference between the vortex and the ambient fluid though. But luckily we can find out the transitional time is A squared. A is the length scale of the vortex, and mu is the diffusivity of the fluid. If I submit the radius of the vortex into this equation, we find out this transitional time Tc is 30 seconds. So because the size of the vortices is macroscopic, I got a transitional time in a time scale of 10 seconds. But if we consider like the powders, like the Brownian particle, the microscopic Brownian particles. If the radius is only 1 micrometer, then I got a transitional time is only 0.3 microsecond.
Okay. So it's size dependent, right?
It is size dependent.
Okay. Okay. So forcing from the rotation. Okay.
This random driven force is from the rotating and buoyancy force.
Okay.
It produces turbulent fluctuations.
Right. More questions? Let me read the chat room. I don't see that somehow. Anybody raise the hand? You can always speak up and ask a question directly. I don't see questions here. At the interface, at the chat room.
Someone raised their hand.
Okay. Maybe.
Tao Jianjun.
Jianjun, yeah.
Please.
Could you please speak up? Ask the question directly. Professor Tao.
Can you try to unmute yourself?
Yeah. Unmute yourself. Somehow this Teams is very new to me, and I tried quite a few times to make it work. Okay.
You try to see, yeah.
Or you type the question in the chat. Yeah, you have to unmute yourself. It's at the top of the very top, next to the cameras, the share. Okay. And Jianjun, if you want to type your question, I can read off on your behalf, if you want. I saw you wrote something. Yeah. Sorry for your system. No worries. We have plenty of time, okay? And in the webinar, we have nearly 1,000 people, 949 people right now. Okay, I read.
Yeah.
Let me read off Jianjun's question. A short question. There is circulation near the wall in the main flow. What is the underlying mechanism? Okay. Yeah.
Yes. Yeah. We can see this traveling wave at the domain boundary, and people call them earlier wormholes.
Wormhole. Okay.
Yeah, that's defined when the bug mode is before the onset of bug mode, when the bug fluid is quiet. But now people also find that this traveling wave also exists, even when at the center we have very intensive convection, and people name them as longitudinal flows.
Okay.
To understand the mechanism for this wormhole formation, I refer to Professor Zhang Keke's series. So that the equation of fluid motion allows allows a traveling wave if you have land-slip boundary conditions, lateral land-slip lateral boundary conditions. But I don't have this theoretical framework on my slides. So if we show the equation of motion with rotations that allow a traveling wave solution, and that's independent on the formation of the central convection. And this wormhole comes into being even earlier than the central convection if you increase Rayleigh number from 0.
Okay.
I wonder if this answer partially Professor Tao's question.
Can you, Professor Zong, could you replay this movie on the
Sure.
current page? Okay. The visualization, this two-dimensional cut was made near the bottom or near the top? That's my
It's
question.
near the bottom. It's at a free height of a quarter times the whole depth from the bottom.
Okay, a quarter height of the whole
Yes.
height. Okay, right.
Yes.
From my naked eye, I can see that the blue circulations, I believe they are downwelling Taylor columns. Is that
Yes.
right? Okay.
Yes.
Because
These are the
they are
cold
heavier
ones.
by centrifugal force, they are moving slowly towards the walls. Is that
Yes.
right? Okay.
Yes.
And then if you visualize the flow near the top plate, if you focus on the hot upwelling flows, do they aggregate towards the middle from the walls? Do they do the
Yes.
opposite?
Yes. If you watch closely, you see some of these inwardly moving warm vortices.
Okay.
But they're weak compared with the strong cold vortices, though. You can see part of this moving inward. See?
Okay.
But
I don't, okay. Maybe near the walls, I see
near the
them
wall.
migrating towards the center, right?
Yeah.
Okay.
In the central regime, they're distorted by the strong cold vortices. The
Okay.
inward motion are distorted a lot.
And any particular reason why the red upwelling flows are stretched, but the cold ones are concentrated as a dot, more better defined? Is there a reason for
Yes,
that?
I think the central fluid is, the background fluid at the center is
Yeah.
relatively warmer because of the centrifugal motion of all particles, all fluid particles. So
Okay.
for the cold vortices, it has a larger temperature, big difference from the ambient fluid.
Okay.
So that makes the points on this cold vortex larger. So we
Okay.
see stronger cold waters at the central regime.
Okay.
And
Yeah.
near the walls, the background fluid is relatively colder because again the centrifugal effects. So the warm waters has a larger, relatively stronger Franz force that makes them stronger. And
Okay.
you see in some regime near the center, they are not quite circular. And the warm waters has this a different type of shape,
Okay.
not circular shape.
Looks like in the future, if you can come up with some cartoons showing these three-dimensional, changes over height, that'd be nice, and over time.
Yes. Right.
Right. It's very nice. It's very nice stuff, especially the ones about finite amplitude perturbation at the bottom, and see how this system responds to that, right?
Yes. That's the last section in my talk.
Right, right. And that response is also very sensitive to the spacing of the perturbation, right?
Yes.
Okay. All right. Other questions?
Yes.
Any other questions in the chat room, or Dr. You can send me some questions from other platforms? Because all I can read is from this Teams, Microsoft.com, this interface.
I not found any questions there.
Okay. Okay, I saw one question. How is the external periodic forcing implemented in the experimental setup? That's an experimentalist question, I guess. By Kai.
So maybe I show you slide like. So we
Okay.
construct on the hot plate some raised cylinders like this. It's 1 unit hot plate, and we embed the heating wires here. So the temperature just above this raised cylinder is the same as the temperature at other place when without the cylinder. So we found the fluid temperature here is relatively hot.
Okay.
And it will induce the upwelling, the warm vortices.
Is that the copper or is it aluminum plate?
It's a copper.
Copper, okay. And you mentioned it's only the extrusion into the fluid is only a few millimeters, right? 4 millimeters?
It's only, yes, only 3 millimeter.
3
and
millimeters. Right.
The fluid gap here is 120 millimeters. So it's only like 2% or 3%.
Okay.
Very, very thin.
All right.
So I don't change my Rayleigh number too much.
That's true. Okay. Okay, I hope this answers Kai's question. And he had another one. How did you decide upon the height of the raised cylinder? You know, I guess Kai's question is about H, right? H.
I define here. See, when there's no raised structure,
Okay.
I define where the fluid depth is. But because this thin cylinder is only 3 millimeter, the fluid height, in fact, is almost the same.
Okay.
It's 120 millimeters.
I guess Kai's question is why you make it 3 millimeters high, not 10, not 1? Is there a rationale for that?
Good question. I try to make this as thin as possible, but I also estimate the thickness of the viscous sponge layer and the thermal sponge layer. So in order to have some modulating effect, we believe that the height of these cylinders should be large enough compared with the thickness sponge layer. And 3 millimeters seems to be the lower limit of the height. So it has certain effect, like modulating effect on the fluid system.
Okay, that's a little bigger than the thermal boundary layer? That's what you
It's
said?
a little bigger than the thermal boundary layer.
Okay.
And it is in the same order as the viscous sponge layer.
Okay, I guess that answers Kai's question. Okay, and Tao, Professor Tao has another question. Considering that the dense vertex columns move to the boundary due to the centrifugal force,
yes,
is it possible to form some horizontal large-scale circulation or patterns due to some instabilities if the flow domain is wide enough?
you see their motion is quite random, stochastic. So there's no order large-scale motion, as I show you in this video. I'm sure your question is very insightful, and this radial motion might induce significant momentum transfer, like angular momentum transfer. But you see this in small scales, and that one forms a large scale like circulations.
Okay.
How they transport the angular momentum is something we want to study in the future.
Okay. Yeah, I guess Tao's question is a tough one. He's asking on the horizontal plane if you could have some large scale circulation or pattern formation, right? That's kind of secondary effect, right? Second order effect. Right.
Right.
Okay.
Yeah, near the top and bottom boundary, we see this circulation though, but only from our DNS, from Dr. Xia's group. In the experiment, we don't have the experimental apparatus to the experimental condition to measure what this feels very close to the boundary, the top and bottom boundary.
Okay.
From DNS, we see this secondary flow.
Okay. Kai says this is interesting stuff. Thank you very much. Okay.
Thank you.
Any other questions? I see no raised hand. Okay. If there's no further questions, maybe we should close the session. Thanks a lot, Qingqiang, Professor Zhou.
Thank you.
I know you're working on some more exciting stuff. It's not the time to broadcast the result yet. I look forward to visiting your lab. Okay.
Yeah. Yes, I look forward to present our new experimental result, collaborating with Professor Jun Zhang in this platform, in this TAML seminar.
Okay, great. Thanks a lot. Okay.
Thank you.
Thank you, Professor Zhang. Thank you, Jun and Professor Zhang. Bye-bye.
Everybody, thanks for your attending this talk, and we appreciate it. Thank you. Bye-bye.
Bye-bye. Thank you.